Hello everyone. I will continue, inshallah, we will continue the second lecture, which will be about multiple integration. This is chapter number 5. It is the last chapter in our course. Finally, it is here. It's really very nice to go through antiderivative. It's another topic with another application and a bunch of problems. I myself like integration so much, and I hope you will enjoy it, inshallah. Our today's agenda, as usual, we will start with an introduction about integration in general. I will try to summarize most of the knowledge that we had previously about integration in the coming couple of slides. Then we will go through double integration, inshallah. So let's start first, before going to double integration, into a quick revision about integration in general. Integration is really a very simple process. It is the antiderivative. It is, I really like the name of antiderivative, which reflects that we reverse all the steps that we do in differentiation in order to get our integrand or function of integration. So I will start with the beginning, integrating, for example, f of x to the power of n times f dash of x, and that's a condition for integration. That's the condition of integration. This is one of the famous laws of integration. If I have a function, as you can see, to the power of n times its derivative, and this is running for every value of n except at -1, the integration in this case will be f of x to the power of n plus 1 divided by n plus 1 plus the constant of integration. Because mainly we are talking about indefinite integration and definite integral, which will develop down the road the double integration. But the first part, which is the indefinite integration, which deals with the integration of a certain function with no integration limits on the integration side. So that's mainly a very important law, as you can see. Also, we can take an example of this law in order to see it in action. Let's say I want to integrate x squared plus 4 to the power of 4 with respect to the x times 2x. If you remark, I'm trying to solve this problem, the first thing to do is to remark that the derivative of this function, which is simply 2 of an x, it is already exists. Once the derivative of your function is exist, then the law is already here, f of x. It has its derivative decided, so all I have to do is to take the main bracket, which is gonna be x squared plus 4. I will add 1 on the power and then divide on the new power plus a constant of integration, and that's how we integrate certain function, as you can see, using this law of integration. Also, it's the same if we use any arbitrary function. So one of the also famous problems that's used using this law is the integration, for example, of a sine of an x to the power of 2 with respect to the x times cosine of x, and it is exactly the same. Because sine square of x, it's exactly sine x to the power of 2. Once this function derivative is already exist, then the integration is gonna be really very simple, which is gonna be a sine of an x to the power of 3 divided by 3 plus the constant of integration, as you can see. As I told you, n goes for any value, real numbers, fraction, rational, whatever, except when n is equal to -1. If n is equal to -1. For example, I want to integrate f, okay, dash of x divided by f of x, which is the exception in the main law. Then the integration will be ln of an f of x plus a constant of integration. And the example on this problem, it's really very simple. You will find the function in the denominator and its derivative on the numerator. So simply something like this, it will be made of, I want to integrate with respect to the x, the value of 2x divided by, let's say, x squared plus 1, as you can see. The main issue is the function in the denominator, it has just only a power of 1. Once the condition is here that the main function f of x derivative is already exist on the denominator, so the condition is already done, then the integration is going to be direct. It's going to equal to ln for an f of x plus a constant of integration. Also, another famous problem or famous example, if I want to integrate sine of x divided by cosine of x with respect to dx, you will find that almost the derivative of the denominator already exists on the numerator, just only missing a negative sign. So if I multiply by a negative in the inside and the negative in the outside, you will remark that the derivative of the denominator already exists on the denominator, and the answer will be negative ln of a cosine x plus a constant of integration, as you can see. So this is law number 1, that's law number 2. They are really very important laws, as you can see. Also, there is another 2 main laws for the exponential function and the logarithmic, for the exponential function in specific, and for the trigonometric functions down the road. For example, if I want to integrate, let's put this is number 3, e to the power of f of x times f dash of x with respect to the x, as you can see. That's the power of the function is f of x. Its derivative already exists. That's a condition. So the answer, it's gonna be e to the power of f of x plus a constant of integration, as you can see. So, and this is this type of integration will be valid just only for the exponential functions. So this law will help you to solve a lot of problems. Like, for example, if I want to integrate e to the power of x squared plus 4 times 2 of an x with respect to x. So once more, the condition is satisfied that the derivative of the power is already exists in here, which is 2x. So the integration will be the main function, which is e to the power of x squared plus 4, and that's the constant of integration, as you can see. Also, if I want to integrate e to the power of cosine of an x times negative a sine of an x with respect to the x, you will remark that also the condition that the derivative of the power already exists, and so the integration will be really simple. It's going to be e to the power of cosine of an x plus the constant of integration, as you can see. Those rules are really very important. It's a direct rules. This is the rule of adding on the power 1 and dividing on the new power. That's the logarithmic function, and that's the exponential function. There is also another law which is famous and usually used, which is how to integrate trigonometry or trigonometric functions, especially with a condition like this one. If the angle was of your function is an arbitrary function, and the derivative of this argument is already exists, then the integration will be really very easy. Another, but also famous example, like if the law which states, I will take, for example, this rule is applied on all the trigonometry or all the trigonometric functions. So I will take the sine or the cosine as an example. So if I have a sine of an f of x times f dash x, if you remark, that's the condition that the argument derivative is already exists. And so if the condition exists, then the integration will be really very simple, which leads to I is equal to minus a sine of f of x plus the constant of integration. Of course, this is cosine f of x, as you can see. And remark the condition on the argument. So instead, if I want to integrate cosine x squared dx and its time x integration, in this case, I will remark that the derivative of the angle is simply gonna be a 2 over x, 2x. But unfortunately, I don't have 2. But in integration, it is acceptable to multiply in a constant and divide on this constant. Or you can take the constant outside the integration sign, which means I will multiply in 2 and divide on 2 in the outside of your integration. And so I will equal to half integrate. So since this condition is already satisfied, I will neglect the cosine and then I will integrate. So it's gonna be a sine of an x squared plus the constant of integration, as you can see. Those are the main laws of integration, and they are repeatedly used in most of our laws. The rest of the examples and the refreshment will happen down the road using and through the problems, the various problems that we will deal with. One huge advantage of this part, and also a disadvantage for this part, it will use all the tools and the information that we had from the beginning of our course. You will see this in the coming parts or the remaining parts of our course. You will find that we use polar coordinates, various coordinate systems. You will see that, we will use them as tools through the problems, using, of course, the rules of antiderivative, as you can see, and also using the skill of substitution and getting the value of these functions with the application and understanding of any function. Do you have a lecture here?
No.
Okay, thank you.
Okay, thank you.
You are fine? So that's the first thing that I want you to know. For this part, we already did go through this analysis. I want to just identify also two main laws, which is really very important, which is the integration by parts. So I will talk now about integration, okay, by parts, because actually we will find or we will need to use this law a lot of times. The integration by parts actually describe the case of having two functions multiplied in each other, as you can see, okay, but there is no relation connecting them, because usually in multiplication of functions, that's a function multiplied in each other. That's a trigonometric function and the part of a polynomial. But actually, there is a relation connecting them, which is the derivative of the argument already exists. But this is not going to be the case in most of our problems. For example, if I have u dash times v dash and I want to integrate, I will choose, I usually like to do it this way, I will choose one of these functions to be integrated and the other function to be differentiated. So I will choose one of them to integrate and the other part to differentiate. I will start with the integration first. So I will integrate u dash to be u times v dash minus the integration or the integral sign. U will go down times the derivative of v dash, which is gonna be v double dash with respect to dx, and that's the integration by parts rule that we can use. It's really very simple, but all you need to do is just to concentrate with dealing with this problem. So once more, if I want to integrate x times e to the power of x with respect to dx, I want to integrate this problem. It's very, very simple. All I have to do is to choose one of these problems to integrate, the other function is to differentiate. So I will use ex to be the integrated part, and I will differentiate x as you can see. So once more, I will equal to integrating e to the power of x, which is gonna be e to the power of x, times the second function will remain the same, unchanging, which is gonna be dx minus integration. The integrated function will go down. The other part of our function, which was not touched, it will be differentiated, which is equal to 1. Then I will finish my integration with respect to the x. So I is gonna be x times e to the power of x minus e to the power of x plus c. That's the integration of the exponential part. This is one of the very famous laws of integration that we will need down the road, as you can see, between the problems that we will move through them. Of course, integration, it's a skill, and it needs an integration between the various informations that we had previously. So it's actually a very important skill, and it needs concentration, it needs good understanding, and it needs training in order to be able to integrate your problems and get the solution exactly right as you see. Okay, let me give you another famous two examples on integration by parts. We usually need them. For example, if I want to integrate x times sine of x with respect to the x, that's a 1. And also another problem which is really very famous, if I want to integrate, for example, ln x with respect to x, as you can see. For x times sine of x, this is clear. These are two functions multiplied each other. So I will choose usually the polynomial part to be the differentiated part, and the other part to be the part that will be integrated. So simply I will integrate sine of x and will differentiate x as you will see. So this will give us I, it's gonna be integrating sine x, which is gonna be negative of a cosine x, times the remaining of your function or integrand, it's gonna be the same, minus integration. The integrated part will go as the integrand of the second integral, so it's gonna be a positive of a cosine x with respect to the x. Then I will differentiate x, which is gonna equal to 1, as you can see. Then I will finalize it, so it will be I equal to negative x cosine of an x, integrating cosine x, which is gonna be plus sine of an x with respect to c, as you can see. For the other problem, I have an issue with ln of x. I can differentiate ln x, but unfortunately, I can't integrate ln x. So I will consider ln x multiplied by positive 1. And so I will equal to, I will choose one of them to be integrated and the other part of this integrand to be the differentiated part. So I will equal to integrate 1, which is gonna be an x times ln of x minus integration. X will go down, then I will differentiate ln x. Differentiating ln x will leave you with 1 over x. Then I will simplify this integrand by eliminating these functions both together, and so I will have I will equal to x times ln of x minus the integration of dx over x, which is gonna be x times ln of x minus ln of x plus the constant of integration, as you can see. This is also one of the famous problems. Just a second. Okay, so once more, as I told you, that's 1 times ln x dx. It will be integrated directly, integrating 1 as an x, ln x minus differentiating both of them together, then finalizing, as you can see. I'm sorry. Of course, this is gonna be simplified, so it's gonna be 1, integrating once more, it's gonna be x. This will grab your attention to something else. You will have to keep your eyes focused on your problem in all times, even me, as you can see. I've tried to simplify these two parts, and I don't know, when I'm writing, I wrote dx over x. So please try to give enough attention while you are working. As you can see, mistakes happen all the time. Before continuing, I want to talk with you about the definite integration. And the definite integration is simply dealing with the antiderivative, but with adding integration limits. So once more, if I want to integrate certain function, as you can see, from A to B, I can do this evaluation of the area by using the definite integration, which is going to be I integrating from A to B for the function f of x with respect to the x, as you can see. And in this case, I will equal to integration of f dash of x, which is going to be f of x. I will replace the x variable by both the integration limits, so it will be f of b minus f of a, and it will be the result, or the value. It will give you a value for your integration. So once more, consider a non-negative continuous function f defined on an interval ab. Suppose that we want to find the area, so all we have to do is to do the integration from a up to b, as you can see, and that's the bottom idea. All the integration laws are applied whatsoever, there is no problem. They are direct using the main integration rules, but just adding for the last step is to substitute by b and a, as you know, of course. And this will give us also the understanding of what's happening through definite integration. Through definite integration, we know that the dark box theory, if I want to evaluate an area under the curve to the axis of integration, I can separate this area by the beginning at A and B by simply getting B minus A over N, and then I will have delta of xi. This guy here, it is delta x1, delta x2, delta of x3, and so on. So if I want to evaluate, for example, this part, I can do it simply by multiplying the average height between the two values at the beginning and at the end of the period times the distance, which is delta x, which will give me the approximate area of this rectangle, multiplying it or adding them on the various rectangles will give me a very close result to the area under the curve. That's mainly the main law or the main idea using the integration. So consider a partition of the interval AB into n subintervals as we did, where A is x node, less than x1, less than x2, less than x3, less than x4, and so on till you reach B. The next step, each subinterval has a length of delta of an xi, so that's a delta of an x1, delta of x2, and so on. Multiplying it by the value of the function at the mid will give you an approximate area of this rectangle. Adding these rectangles all together will make you capable of having or evaluating the area under the curve. Of course, as long as, the less or the more the number of points that you're distributing your interval on, the increase of the accuracy of your function. So this is, for example, a 1, 2, 3, 4, 5. If you divide to 5 rectangles, this is if they are 10, this is if they are more than that, you will find that the value is really very close in evaluation. And so using the Riemann law, I will be able to evaluate the area under the curve using the summation notation of f of xi times delta xi, as you can see exactly. And that's Riemann integral, which defines the definite integration from a to b for f of x dx. It's exactly taking the limit of n tends to infinity for a maximum of delta x equal to 0 or tends to 0 for f of xi times delta xi. So these rectangles will have a very tiny width and they will be very close to the integration interval, as you can see. If we are talking about a rectangle area, and this is AB times CD, integrating the double integration will give me the volume of the function under within this region. So actually integrating f of xy dA, I'm integrating with respect to the region that's covered by all of this, it will give me, or it will develop the volume of integration using the same concept as I told you. That's a more detailed explanation of the summation notations and how it did work in both the x direction and the y direction in evaluating each rectangle prism of these rectangle prisms, each beside each other, and so you will be able to get or to imagine the area of the complete volume that's enclosed by the function and the region that you are integrating to. So Riemann double integration, and that's the double Riemann sum relation that controls the value of the double integration in general. So once more, Fabian theorem for rectangular regions, which states that if I want to integrate a function f of xy with respect to dA, starting from C to D, okay, within a function, with the direction of dy first, then the direction of dx, it's exactly the same for the same region. If you change it, the order of integration to do dx first, then dy. So for a rectangle area, AB cross CD, be a continuous function on this region, then f is rectangle, integrable function in R, and then that's the Fabian's theory, as you can see. Fabian theorem converts a double integral on an integrable region into two sequential one-dimensional integral intervals, which means I can integrate each one of them separately. So I will integrate first. It's like differentiation by parts, integration by parts. I will integrate first with respect to dy, then the result will be integrated with respect to the x with the same concepts that you understand or you know for the differentiation by parts and vice versa. Also, the double integration accepts that it can be distributed on, because it's mainly an integration, so integration can be distributed on addition or subtraction. It's exactly the same. A constant can be taken outside the double integration side, and if you have f of xy less than or equal g of xy for every xy belongs to D, then the function in the double integral, it will be less than the value after the double integration of g, which makes sense exactly. Now I want you to understand that multiple integration extends the concepts of single variable integration. That's what I'm trying to tell you. Two functions of more than one variable in R2. Double integral are used to integrate functions of two variables over region in the plan. So mainly for the function from R2 into R, I can use double integration successfully. That's double integration, that's the element of area that we will integrate to. And once more, the function xy and doing or performing this integration will develop the volume using the double integration, as you can see. That's once more explanation that I can reach the area required not just only by one integral, but more than one integration, as we will see in the coming periods. So if I want to evaluate the area under the curve on this region or the volume of these parts, I will have to separate the area of integration into two regions and work with them. This is actually came before its suitable slide, but we will see progress on this issue more than once, and it will be described very well in the coming lecture, inshallah. I want to give you the iterated method, and I will stop by here for today. I will continue tomorrow, but I will go through this slide in specific. So if I want to integrate dx dy versus dy dx, it's very, very simple. So if I want to evaluate the integration for f of xy with respect to an element of an area, I can go dx first, then dy, by simply remarking the following. If this is the x-axis, and that's the y-axis, and these are the functions which are the first function, a, which is x1 as a function of y, f1 of y, and till the second function, which is b, x2, y, which is equal to f2 of y, and in the other direction, the region starts from c up to d. That's the region of integration. So actually, that's the region that I want to integrate in, which is between the entrance and the exit of our region, and starts from, as you can see, this is from C to D. If I'm integrating dx dy, this is gonna be the first direction, and that's gonna be the second direction. The first direction will start from x1 of y up to x2 of y, and the second direction will go from C to D in order to evaluate through the region, as we will see tomorrow in our next lecture, inshallah. I can also, instead of integrating in the direction of dx dy, I can integrate in the other direction, which is y dx, as you can see. Here is x and y, and these are the two functions. That's my entrance, that's the positive direction. So that's the entrance, and that's the exit, and it will be integrated from A into B. So I can identify the region of integration by dy first. I will perform the first integration in the direction of y. So I will enter from this function and get outside from the exit function, and my region will start from A till B, as you can see. These are the two functions of, that's the second direction from A to B, as I told you. That's what Phillian method states. Tomorrow we will see problems on this. This is for the first direction, second direction, and that's if I replace them, dx first, dy. Here's dy dx in the first integration. Also, I will need, as you will see, to move between them. I will leave this for tomorrow, and I think today it's fair enough that we already did go through these two lectures together. Please try to go through them. I will try to upload them as fast as possible. And tomorrow I will continue, inshallah, on the double integration and its application tomorrow, inshallah. Thank you very much for listening and for attending this lecture, and wish you the best of luck, inshallah. Assalamu alaikum.